came, and in fact I will not be, but I'm just here to introduce Don. So it's a real honor for me, to have the opportunity to introduce Don. I think his accomplishments are probably well known to the people in the audience. The work in programming languages and computer theory, algorithms, on tech, and many other things, that extend way beyond computer science. I thought, what can I say that people wouldn't know? And so I thought I could talk a little bit about my experiences with Don over the years. And so I just, just a few brief mentions of how I've known Don, through my career. So I first met him, but only virtually, when I was 20 years old, and I got this book that I was supposed to read on algorithms. And I could not believe the amount of material in that book and how anybody could possibly know all this stuff. And then I found out there was more than one book. And that really surprised me. So I thought I will never master all of this material. And then I eventually realized that actually probably Don's the only person who knows everything in all of those books. At some point in my life I realized that. And then when I came to Stanford in 2003, I actually got to meet Don in person. We may have met earlier than that, may have crossed paths, but actually when I joined the department, Don was obviously a very senior figure in the department and always had kind words for new people. And so that's when I actually got to know Don personally. And he did many kindnesses over the years. I just mentioned one. My kids appear in one of his books. So Don used my kids as models in one of his books, and there's several pages of their photographs. And he gave us, my wife and I, a signed copy of that book, which we treasure. Then there was an event, maybe only 3 or 4 years ago, when Don came into my office and said he had read one of my papers and he had this technical question, and about this paper I'd written a couple of years before. And being a slow thinker, I think I answered it extremely poorly on the spot. Don, he had actually studied the paper and understood the issue at least as well as I did at that point in time. But he was very generous and didn't push me too hard on that. And then I think, in my time as chair, there's been a number of times when Don's taken me aside and just given me, a sentence or two of advice about, how to handle, shall we say, some difficult situations in the department, and I greatly appreciate that. So anyway, that's a little bit about my experience with Don. He's been, a wonderful colleague, obviously a great scientist, and a beloved figure here at Stanford for a long time. And it's a great pleasure to introduce him for the 24th Christmas lecture. So Don.
Okay, well, thank you, Alex. I can't justify that all, but let's get on with it, because I got a whole bunch of stuff to say. I still see 3 empty seats up here and a nice place to sit on the floor. Here's another one, 4. So, unless you plan to leave early. Okay, so the title today is Dancing Links. And I told my friend that I was going to talk about dancing links. He said, "Oh, didn't you talk about dancing links once before?" And sure enough, I'd forgotten about it. But in 2000, in February of 2000, I gave another one of these talks. It was before this particular room was built. And it was called Dancing Links then. Well, an awful lot has been learned since then. So I'm not going to repeat very much of what I said 18 years ago, but you can still find it on the website of SITN. It shouldn't be too hard to do, and then you'll see what the difference was that 18 years can make. Now, next thing I want to show you is this, which is the cover of a book that I was hoping to get ready for Christmas, so that people could buy it. However, I kept discovering more and more stuff about dancing lynx, and so it was never time to finally wrap it. So early next year, this will definitely be coming out. I have to. It's already up to 350 pages, and I was going to, these little paperback fascicles, I was going to try to keep the limit at a max of 300 pages, but it actually comes before this one. This is the one that I published a couple of years ago, and these are eventually going to be. This will be the middle third, and this will be the first third of volume 4B of the Art of Computer Programming, and this is volume 4A. So okay, so I'm still working on it, and until I go senile, I continue to keep on chugging out content, even though I can't remember anymore what's in it all, locally I have a good knowledge of each page of these books. Now, and by the way, I have this other book called Selected Papers on Fun and Games, which is a really great book to give for Christmas. And in that book you can find pictures not only of one but two of Alex's delightful children. So. Another reason to buy the book. Okay, so now here we are. What is dancing lynx? Tonight I'm going to talk about a few things that are technical, but mostly it's show and tell. Mostly it's things that that you can look up later if you want to get more information. But I'm not going to I'm not going to really dumb it down either by omitting what the main point is. But first place, dancing lynx is an extremely simple idea about something that a way to write computer programs that is so simple that at first you might say, how could anybody talk for more than 5 minutes about this idea? However, as I said, already 18 years ago, I talked an hour and a half about it, and tonight, I'll try to get into an hour and a half. So what is it? So I got to first describe the idea, then something about it, but then lots and lots of applications about it, because it turns out the reason I haven't finished this yet is because I keep finding new. It's like at Christmas time, I'm like a kid with a new toy, because I have this technology of dancing lynx that I can use to solve problems that I never thought I would solve in my lifetime. So it doesn't solve every problem. I mean, but on the other hand, it's completely orthogonal to deep learning. I don't think any of the things I'm going to talk about tonight are. So in the first place, it relies on doubly linked lists. There's a version for singly linked lists, but links. By links, I'm thinking about the pointers between elements of a list, and so we have a doubly linked list. Let's suppose we have a doubly linked list with 4 nodes in it, and then with a doubly linked list, we usually also have a header node. So I'll call that 0, 1, 2, 3, 4, where 0 is the header node. And then it's doubly linked, so 0, so everything points to its successor, and the successor of the last guy is the head. And then everything also points to the predecessor, which so these. I already drew that guy, and this comes back in here. So in memory, then if we had locations 0, 1, 2, 3, 4, and we have L link and R link, then L link of our link of 0 is 1, and this is 2, this is 3, this is 4, this is 0, and then going back, 4 points to 3, to 2, to 1, to 0, and to 4. Okay, so this is the way it looks in memory when we have a doubly linked list. Now, okay, one of the main reasons why it's nice in lots and lots of programs to have doubly linked lists is because we can delete a node from the list just knowing what node it is. We don't need to know how we got there. We can, if we know the address of a node P, we can say delete P. So delete P is a very simple operation. I set L to L link of P, and R to R link of P, and then I set R link of L to R, and L link of R to L. So that wipes it out because the L was the predecessor, R was the successor, and now the predecessor points to the successor points to the predecessor, and that's it. So this is this is kindergarten stuff. But the thing about dancing links is that for I don't know, for 30 years when I wrote programs, I thought, okay, now the good thing is to do is clean up and reset the links of P. P is no longer in the list, so I return it to the pool of available memory, and clean it up. However, there are lots and lots of applications where actually I know that everything I do, I'm going to want to undo later on. So many interactive applications, and the backtrack application like we were watching on before the lecture. When you're backtracking, you make a decision, but that's a tentative decision, and then if it was the wrong decision, you backtrack and you undo, and you go back to where you were before the decision. So this is where what I'm going to tell you about really shines when we're undoing something. And so to undo a deletion, we would insert P. And for this, we say L goes to L link of P, R goes to R link of P, and then we say R link of L is P. And now what could be simpler than this? L link of R is P. So this obviously undoes what I did before if I did this right after that one. So, however, I wouldn't have been able to do this if I had garbage collected, if I had cleaned up my memory, so let's just take a look at it. Suppose for example I delete 3 from this list. Okay, so I want to. I want 3 to go out, and so that says that L is 2, R is 4, so I have to change this to 4, and I have to change this to 2. Okay, so 3 is out now. And then, let's suppose I also delete 1, and so now I delete 1, so it's 0 and 2 have to change, and so when this guy goes out, I have to change this to 2, and I have to change this to 0. And suppose I delete 4. Okay, so 2 and 0 are the predecessor and successor now, so I have to change this to 0, and I have to change this to 0. Yeah, okay, so I've deleted those. Now, undo. So now let's say insert 4. But before I insert, I want to emphasize that the current status of these links is really a mess. One of the main paradigms for proving that a program is correct and for knowing that your algorithm is working is what we call invariance of the data structure, where we say for every part of the data structure, what does it mean? So what does L-link mean? What does R-link mean? And we give some invariant relation which is supposed to stay true all the way through our computation. And when I do something like this, the invariant becomes hopeless. I mean, you could describe it in logic, but it doesn't correspond to anybody's intuition. It's so complicated. Nobody wants to bother writing down what this invariant is. So it opens up a whole new way of proving that programs are correct. I'm not saying invariants are bad. I'm saying that they aren't enough to prove this kind of algorithm correct in the right way, because my proof of correctness is operational rather than through logic. I'm saying I'm not going to tell you what L-link and R-link mean. All I'm going to tell you is if you do the insertion operation in the opposite order than you did the deletions, you're going to get back what you had. So I'm not telling you what it means. I'm telling you operationally what it does, and that's convincing. But don't ever ask me to prove this method correct by the old style of invariant. Okay, now so if I insert 4, then I look here at 2 and 0, and I says, oh yeah, okay, I should have crossed these guys out, but I can look at 2 and 0, and now you see I haven't erased that, so I still remember what was the predecessor and successor of 4 at that time. So I can go back now to 2, and I can change this back to 4, and I can go back to 0, and I can change that back to 4. Okay, and I don't have time to do, but at this point I could delete 2, and then then I could insert 2 and insert 1 and insert 3, and I'd be back to my starting point. But the intermediate points, don't ask me what they were. Okay, so now this, as I say, is extremely good for well, the main point of it is undoing, and one of the sort of corollaries is don't clean up your data all the time. There might be. Some people leave it in there only to see what afterward if there was some hacker attack. How did it happen? But here there's a virtue in being sloppy. So okay, now take a look at the video from 18 years ago and see how I explained it then. Okay, now. One of the most natural applications of this is for a particular kind of problem that's called the exact cover problem, and for 10 years this was the only kind of problem that I used to use dancing links for. So the exact cover problem is one of the traditional standard problems of computer science that Dick Karp showed in the 60s is NP complete, and I always used to think of it this way: as I have a matrix of zeros and ones, and here's a particular one that I've used in examples in my book. I'm going to write 2 more lines here. The idea of an exact cover problem is that we have this matrix of zeros and ones, and we're going to choose some of the rows, just a few of the rows, in such a way that when we add those rows up, we get 1, 1, 1, 1, 1, 1. We get exactly 1 every time we do. So that's the goal. Like I'm going to have to choose either the second row or the fourth row because I got to have a 1 here. So let's suppose that I tried to choose the second row. Okay. So that means I've covered column let me put names on these columns, A, B, C, D, E, F, G. So I've covered A, and I've covered D, and I've covered G. And so there's just about only one decent way to solve an exact cover problem, and that is to try trial and error. You know, try something, and then you're left with an exact cover problem that's simpler because you've already covered some of the stuff. So in this case, we've covered A and D and G, and so all I have to do is look at the remaining columns in the things that haven't been done. So, for example, this one now I've got B, C, E, F is left. So I have 0, 1, 1, 0, and then this guy gives me 1, 1, 0, 1. This one I can't use because it clashes in A. This one I can't use because it clashes in G, and this one I can't use, it clashes D and G. So so if I choose this guy, then I have to cover the other 4 columns somehow out of these, except that I didn't copy this very well. This is a 1, right? It's certainly going to be hard to cover B if there's no B, if there's no 1s there. Okay, so but still, pretty soon you see that there's no way to cover this because each C interferes with the other guy. So that isn't going to work. So we're going to have to backtrack and say, no, I'm not going to choose this one. I'm going to choose this one instead. All right, now. Let's pause for a minute to look inside the computer because if we're using dancing links, okay, let me show you. Let me show you what I got written so far. So this is a draft of the of what I've got online now. Actually, there's no link to it online, but there are links. There are links. Fascicle 5 has 3 parts to it, and there are links to the first part and the second part. And the first one is called fascicle 5A. The second one, fascicle 5B. So if you change that link to fascicle 5C, you're going to get a look at this. Right? And in a month or so, I'll have a link to it because I still haven't made the index to this and so on. So this is only for the people who are really courageous. I can't wait. But now we get to the. Oh, by the way, yeah, there's a. I'm not going to take time to zoom in on this, but find any errors in this, you get 256. So it helps pay your tuition. Now, so you see the pictures of doubly linked lists here and so on. Here's that very same matrix, and here's the way it looks in. Let's see. I got to learn this technology now. Okay. Whoa! I turned off the machine. I hit the power button by mistake. Okay, so yeah, that's a little bit of a danger. Okay, so so in memory, let's zoom in a little more. Yeah, my book is interfering with the. Okay, I'll have to zoom. Yeah. Okay, so you can't see it too well. Tell you what. Bind it. Okay, so all right. I have page numbers on here. I can get this back in order again at the end. Okay, so here we. Okay, so this is the way it looks in memory, and everywhere there was a 1 in that matrix, I've got a node. and then the columns A, B, C, D, E, F, G are doubly linked. So everything has a pointer instead to left and right. It has a pointer up and down. And in the columns themselves, there are also pointers to the left and right. So these guys have 4 links. They're doubly linked horizontally and vertically both. And that's the list of columns that haven't been covered yet. But the vertical lists are to all of the ways of covering that particular guy. And in the old days, I also used to doubly link the guys in the individual rows of the matrix, but it turned out those links were never changing, so there was no point in doing that. I just keep it sequentially in memory. So I have nodes 16, 17, 18, and then each possibility has a spacer node before and after it that tells you how to get to the end of the list or to the beginning of the list if you encounter a spacer node. So this is a faster data structure than I had 18 years ago. But the main idea is that I've got the exact cover problem, and it's sitting here as a bunch of nodes in memory that have links between them. Okay, now so if I decide to cover column A, that means that I'm going to take out of the theta structure every row that had something in A. So I'm going to take out this line. I'm going to take out this line, and so I march through. From 12, I go to 13. I say take 13 out. So that's a delete operation. Delete 13 from its doubly linked list. Delete 14 from this doubly linked list. And similarly, this one, I'm going to delete 20. I'm going to delete 21 and 22 from their list. Okay, so in other words, no matter what I do to cover the A, I'm going to be deleting all of these entries from the list. Now, when I actually decide, however, that I'm going to try this one as the way to cover A, then I also have to cover column D and cover column G. As I cover column D, that's going to tell me I'm going to have to delete node 27, and I'm going to have to delete the row that contains 27, and I walk down G and see what's still left in G, and I see these 2 guys, and so I'm going to have to delete this line. This one has already been deleted. So anyway, looking inside, following one link after another, you see what you have to remove from these lists. Later on, when I'm going to undo this operation, all of those links that I looked at are still there. I haven't garbage collected them away. They're still sitting there. And so later on, when I want to undo this operation, I can say, I chose 11. I looked at covering G. Oh, that means that I have to uncover G. And so it tells me, oh yeah, put this guy back. And I did my deletions from left to right. So when I undo, I go from right to left. But all of those links are still sitting there. And so I didn't have to store a single new thing in memory in order to undo this complicated removing from list to list. I'm walking through lists that didn't exist before, and the list jumped back into place. Something like opening a zipper or something. Just before I need another link, it's there and it's valid again. So this is a way that you can walk through an exact cover problem and delete, insert, and they never mess each other up. When you look at it, it just seems that these numbers in the computer are following an elegantly choreographed dance. And so that's why I call it dancing links. And I'm still waiting for somebody to write an app that takes this algorithm and an exact cover problem and somehow animates it. And so you can see these things. I mean, as I'm debugging, I watch it happening and I marvel at it. But I wish I had a good visualization of the process. Okay. Any questions about this? The main point is that even though the idea is extremely simple, that one operation obviously undoes the other. The fact that I didn't remove the stuff from memory means that all the scraps of information that I need to take me back are there, and I keep changing them, and the ones I needed second last become available after I've done the last, and after I've undone the last, et cetera, et cetera. Okay, so that's the basic magical idea of dancing links. Now, so let's take a look at some applications. The easiest step, well, first I want to mention that I found out that there are so many applications and I decided that as years went on, I didn't want to think of this exact cover problem anymore as if it was a matrix of zeros and ones. I mean, I love zeros and ones, and as a mathematician, I've played with matrices of zeros and ones for years. But it turned out that there's almost always a really sparse matrix, and it's much better if I had some other way. So instead of talking about rows and columns, I talk about options and items. And so these A, B, C, D, E, F, G, I call these items of my problem, and then the various ways to cover the items I call options. So we have options, and for example, the first option is CE, and the second option is ADG, and the third option is BC, the fourth option ADF, and two more options BG and DEG. Okay, so instead of presenting my data as zeros and ones, I present it instead in a text file as lines of options, and the things in the option are, I call them items. Okay, so now I can actually talk about problems in which items are rows instead of columns. For example, I mean, I sometimes the terminology for all the applications of an exact cover problem will change from application to application, but in every case, the word option has worked out well, and the word item has worked out well for the way to present it. So the very simplest exact cover problems are the ones where there's only two items in every option. If there's only one item in an option, that's even simpler, but that's so trivial. The main interesting ones start when we have at least two items per option, and the case where there's only one, actually, we have a shortcut to handle those. And those are exactly the problems that everybody knows under the name of perfect matching in graphs. If you have two items in an option, you can think of that as a graph with where that's an edge between those two items. And so if we want to choose, so that we've covered every vertex exactly once. That collection of edges where every vertex, that's called a perfect matching of a graph. And in general, a matrix of zeros and ones is called a hypergraph, and the rows of a hypergraph are called the hyperedges. And so this exact cover problem is the same as the problem of getting a perfect matching in a hypergraph. Okay, so the case of ordinary graph, where there's two, one of the most beautiful examples of a perfect matching problem is it is called the a problem made popular by Edouard Lucas in the 19th century, and they call it the problème Ménage. This is the problem of couples. And so if you look in Wikipedia, you get a very beautiful picture about the problème de ménage. The idea is you have n male-female couples, and you want to sit them at a circular table. So in this picture, n is 5. And so we got 10 seats at the table, and the rule is that has to alternate male, female, male, male, female, and nobody sits next to their spouse. So how many ways are there to solve the problème de ménage? In this case, there's also a problem of how do you get a pink napkin for this place over here. But anyway, it's a nice picture. This is a really kind of a nice practical problem. People face it all the time if they have a circular table, and also there's beautiful mathematics that goes with it. What more could you ask? But let's take a look at it as I would set it up as an exact cover problem to my solvers. So I have a bunch of solvers that I call DLX. Some of you will know DLX as the name of the machine that Hennessy and Patterson use in their book on architecture. I had MIX, and they wanted also to have a machine that was Roman numerals. So DLX is 560 and MIX is 1009. But anyway, now DLX is actually, DL stands for dancing links here, and X for exact cover, and so here's a example data file, and it's produced by a program called Ménage DLX with the parameter 5. At first it states the item. So the first line of a file as input to a DLX solver states all of the items. And here I have items S0, M0 through S4. For there are 5 seats that have to be covered, and there are 5 men that have to be covered. Right? I'm going to assume that the women have already been seated somehow. No matter how we solve the problem, we're going to have the women are going to occupy these alternate seats. So let's suppose that there's lots of ways to there's 2n factorial ways to do that, but let's suppose that's already been done, because no matter what happens, we have to solve this residual problem after the women are seated. So here we have then I have W0. The women are already sitting there, but there are 5 seats between them: S0, S1, S2, and so on. And then I've got to cover the 5 seats, and I have to also cover them with 5 men, M0 through M1. And so these are the people. And now, what are the options? So we got these 10 options to cover I'm sorry, the items, 10 items to cover, but the first option is S0 M1. So man 1 can sit in S0. Man 0 can't sit there. Man 4 can't sit there because they're not allowed to sit next to your right. So S0 M1, S0 M2, S0 M3 are the options for S0. Then there's options for S1 and so on and so on. And I could have listed these options in any order, but these are the possibilities for the exact cover problem. And so you make a doubly linked list inside the computer for this, and let me okay. Let me see where I am in my. Yeah. Okay. Here I am. Okay. And so. Feed it to my solver, and out come the answers. And so it turns out there's 13 solutions to this problem. And let's just take a look at a typical one, solution number 8. Okay, yeah, so solution number 8. So this says S0, M0. This was 2 of 3 ways to cover S0. So we've already tried the first way. And and here it is. It works S1, M4. Then this one says M3, S2 instead of S2, M3. It meant that at this point, it says one of one. It meant after I've seeded S0, after I've seeded M2 here and M4 here, there's only one place for M3 to go. So it chose not to cover one of the S's, but it looks at every item. There's no difference between the M items and the S items. The one that has the fewest possibilities is the one that we try to cover next. And so that's the way this particular solution came out. So as I say, there are 13 solutions, and how did I get that? Well, for example, here I tried for 3, 4, 5, 6, 7, 8, 9, 10 couples. Each case I called my Menage DLX to generate the data, and then I pipe it in. I fed it into the DLX1 solver for exact cover, and then I said, okay, I have an echo statement, so I can separate these out. So here's the. So first of all, 3 men, 3 women. There's 3 options, 6 items, 9 total entries among the items. Because there's 3 options and 9 entries, but there should be, that should be 6. So what did I do? That's interesting. Why did that say 9 entries? I'll have to check that out. Okay. Okay. Now, with 4 couples, we had 8 options. With 5 couples, we had 15 options. And it seems to think there are 3 entries instead of 2 for each option. So that there's off by 1 somehow. They probably counts something for the spacer. I don't know why. Okay, so we get 13 solutions. With 5, we get 80 solutions. We get 579. When there were 10 couples, 439,000 and some solutions. How long did it take to find these solutions? And all of the algorithms in my book, I could tell you how many seconds it took, but that wouldn't mean anything next year. Because computers keep changing from year to year. So instead, I count how many references to memory were made, and that's not going to change. I mean, you can change the algorithm and find another, find a better way. But this particular method is going to read or write memory a certain number of times, and it turns out that. For example, in this 10-couple case, about 180 memory references per solution. So it's piping out these, not having to do much computation between solutions. These solutions are generated internally, and they could have been piped to a file or something if I wanted to, but in this case, I only counted them. Okay, any questions like that? Yeah.
Do you have a comparison of with some other algorithm that would have taken?
Comparison with other algorithms? Yeah, I'll get to some of that, but because of course this is a general purpose solver, and when you get to perfect matching problems, there's all kinds of different ways to solve perfect matching problems, as we know. What?
Have you found a correlation between memory reads and clock cycles?
Yes. It's not, it's not real tight, but and there are some problems that are more cache friendly than others, obviously, but this I write about 5 new problems a week, and it's been pretty steady for the last 10 years. The number of them, but if I do, but in my book, The Stanford Graph Base, I have I compared 6 algorithms or something for a minimum spanning tree, and they used caches in different ways, and so the cost of a mem per microsecond was definitely different in different algorithms. Yeah. Okay, good question. I got to move on to dancing link stuff. So this DLX solver I'm talking about, it is on the web. There's DLX1, DLX2, and so on, and you can download them from my homepage. And it not surprisingly written in C Web, which is my favorite programming language, and you've got all the code in here. It starts out with, in fact, an example, to the very same example, it explains the input data and the various bells and whistles you have for running it. A big part of the program is just inputting the thing into the doubly linked list in the first place. Then we get the actual covering. So here's the cover subroutine, and it does the doubly linked lists, and does a deletion here, and then there's an uncover which does the insertion operation, and so on. So that's the program that you can take a look at. Now, among the bells and whistles, I can say, for example, well here I tried it out on 16 couple. So I menage 16, and the DLX1, and my first parameter is M1 billion, and so just show me every billionth solution, and then T1 billion that says stop after you found a billion solutions, and then S says this is randomized. When you're choosing between different options, choose, scramble the lists and do it randomly and see if that makes a difference. And this is the seed for a random number generator. If I change the seed, I would get another random one. And then, okay, so now standard by default is that every 10 billion mems, it gives me a status report. When you're running a combinatorial problem, you don't like to just sit there and see. You want to know how it's doing, and so about every 20 seconds, this is right now on my computer at home. That 20 seconds is about 10 billion mems. Okay, so it had found 52 million solutions during those first 20 seconds, and then it said, well, at the top level, it's doing case 1 of 14, 1E. The E is hexadecimal, so case 1 of 14. So there were 14 ways to cover seat 0, probably. And then after I did that, there were 13 ways to cover some other seat, and then 12 ways, and then so I'm still working on the first. By the time I'm down here, I'm still on the first choice for the first option and covering this one, but then I'm up to the 9th choice of this guy, and so you can watch this and you can see how far you are, and also there's a number at the end that tells you percentage-wise how far have I gone. So at this point I'm up to 0.0003. Now, actually, the number of solutions to the Menage problem is very close to n factorial divided by e squared. E squared is between 7 and 8, and so this is one out of every 6, between 1 out of every 7, 1 out of every 8 permutation actually works for this problem of seating people without being next to their spouses, and so if you work out what's 16 factorial, it's I think it's 21 trillion, and so you divide that by 7, you get 3 trillion. So there's about 3 trillion solutions. And I said stop after the first billion. So anyway, that's where we are. Okay, now. And it would grind them out, and I'd have them in less than a day, if I really wanted. Without randomization, this was going at 190 MEMS per solution. I'm sorry, yeah, 192 192 billion MEMS in order to get 10 billion solutions, so or 1 billion solutions, and so that's about 192 per solution. But it would have been 175 if I hadn't used randomization at every step. That's, I had to generate random numbers. That takes a little time. Okay, so there's an example of how I use this on one of the simplest problems, the simple problem of a perfect matching. Let me go next to a classic problem of computer science, the one we were watching on the movie before it came in, the problem of n queens. Here we're trying to put queens on a chessboard. The classic problem, we have an ordinary chessboard and 8 queens, and so I want to get eight queens on the board so that neither queen attacks another one, and so now I set this up with another program called Queens DLX 8 to get the 8 queens problem, and it sets up. It sets up the items R4, C4. This is a rank and column on a chessboard, and I put them in this order, starting in the middle of the board and going to the edges because it's a little faster to decide on the queens in the middle. But the interesting thing is that rows and columns are symmetrical. All of the textbook solutions to this problem go row by row. You first put a queen in row 0, then row 1, or some row or other, and you try different columns. But in this case, sometimes it's better to choose a column because there's only a few ways left to. A few empty spaces left in that column. So instead of going row by row, this approach by options doesn't distinguish between them. But then they have this vertical bar here, and so there's secondary items that come after the vertical bar. Secondary items, you don't have to cover them, but you're allowed only to cover them at most once instead of exactly once. And so a secondary item, these are for the diagonals. So in the queens problem, I've got 8 rows and I've got 8 columns, but I've also got 15 diagonals going this way and 15 diagonals coming this way, and so here's an option. For example, R2 C5 A7 BA. This is R2 C5 B10 and A7. So it says that I can't occupy a diagonal more than once, but I don't have to occupy a diagonal exactly once. Okay, so in this case, some of the options have only 3 items, but most of them have 4 items, and so that's the n queens problem. Another nice example of exact cover, and so here I tried it for up to 16 queens. 8 queens up to 16 queens, and so 8 queens. There's always 92 solutions, and so on. You get up to when I get up to 16 queens, it hasn't solved them all. By default, it gives me this progress report after every 10 billion MEMS. So I got here. I was in case 4 of 16 cases after 10 billion. It was finally at the end. It took a minute and 16 seconds to get all of the 15 million solutions to the 16 queens problem, and this compares favorably to special purpose algorithms that are written. Of course, the world champion solution to the n queens problem. Gosh, I forget exactly how far they got. But anyway, they built an FPGA series and so on. They made it massively parallel and squeezed everything out. Okay, next problem. You might recognize this was in the Palo Alto Weekly a week ago Friday, and I got to talk about Sudoku because this is one of the great simple things to do with this exact cover algorithm. So Sudoku, I don't know. Some people say it's the most popular recreation in the world at the moment. Anyway, this was the problem we had in last week's weekly. So here it is as a I have Sudoku deal X, and it puts out a whole bunch of items here. I didn't want to list them all, but there's an item for every empty cell. There's an item for every row, every number that hasn't appeared in a row or a column or a box. If we take a look at, for example, these two options here, can you see that? This is P85, R81, C51. This option corresponds to putting a 1 in row 8 in column 5. I'm numbering from 0, so that would be the bottom row, and in this column. So that would be like putting a 1 right here. And the next option is for putting a 7 in that place. So that would say, cover. Put something in P85, put your 7 in row 8, put your 7 in column 5, and put your 7 in box number 7. So that would be one of the options. And after I've solved the problem, I'm going to have exactly one option for P85. I'm going to have exactly one option for R87. I'm going to have one option where I chose a 7 in this row. I'm going to have one option where I chose a 7 in this column, and one option where I chose a 7 in this box. Okay, so exact cover problem. Okay, so this this cruises to victory incredibly fast. So if you look at the solution to the problem, it said, well, there's only one way to fill P33. And after you filled that, then there's only one way to do 43, and so on. There was only one choice. There were never had to, you had to stop and think. All you had to do was would go down. In fact, that particular problem, there was also only one way to put a 3 in column 1, in row 1, or in row 5, or only one way to put a 4 in column 1, and so on. There were all kind of force moves, waiting for you to do. So it turns out that if you look at over the years, I'm on an airline. I look at a magazine, or I might see in the London Times or wherever I am. Every once in a while, I took a sample of the Sudoku problem that they were doing, and it ranged from problems that were called, diabolical and impossible and so on. And I never found one that needed a search tree of more than 280 nodes. And it's almost always, really fast, even with the limited heuristics that are in here. Well, I got a lot more to talk about those, so I can't dwell on it. But I do want to mention that since Sudoku is such a popular problem, I do have some pages about it, and here's for example. A Sudoku problem where the clues are 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7. It has the first 32 digits of pi, since my Sudoku solver is so fast, it wasn't hard to interactively do this. I thought this was an original idea, but I learned earlier this year that Johan de Rutter had already done this 5 or 6 years ago. Johan, are you here tonight? Yeah. Oh, here you are. Yeah. Okay. So, and I thought he lived in the Netherlands, but I got to meet him a couple months ago. I think you know that over the years, whenever I have to choose an example in my books, I try to base it on pi if I can. And now the next one here is 3, 1, 4, 1, 5, 9. It's not perfect, but it has only 17 clues in it. it's known that that every pseudoclue with a unique solution, you need at least 17 clues. So this one has only 16, and so it's got to have 2 solutions to it. But it turns out that it doesn't use either a 7 or 8 anywhere, and so those 2 solutions are exactly the same, except that you switch 7 and 8. Okay, so anyway, lots of interesting, fun things to do about Sudoku, and I discussed how it corresponds with the dancing links algorithm. And there's jigsaw Sudoku, which is where I, instead of having 3 by 3 boxes, you can have the boxes be arbitrary size. And here it turns out, okay, here's pi, giving a unique solution with the jigsaw Sudoku. All right, now. But exact cover problems go, to many other cases, and one of the first that I knew about were problems like polyominoes. How many people have heard of pentominoes? Anybody? Oh, we got about 1 out of 4. Okay, so this was all the rage in the 60s, taking these shapes and packing them into rectangles. How many people know about the Soma cube? Not as many. So the Soma cube is a 3-dimensional toy where you're supposed to pack these 7 pieces into a 3 by 3 by 3 cube. And this was such a popular. I mean, there were more than 2 million Soma cubes in America alone in 1970. This was, before Rubik's cube. This was the cube, and I brought my set here tonight, but I don't have time to. But anyway, I'm very proud of this because I got it in Denmark. It's beautiful rosewood pieces. And just as I was setting up on a desk here, I found out that this one came apart. But anyway, lots of it's actually how can I say it? It's a pleasure to play with these things, and so one of the greatest mathematicians, John Conway, spent a lot of time figuring all kinds of neat things out about Soma, and also these have lessons in general for exact cover problems, because as I point out in the next few pages, by reasoning about, there are a lot of tricks you can apply to exact cover problems to simplify it and throw out a lot of options. And so, in particular for the Soma cube, it turns out that you can prove, for example, that that this piece has to go on an edge, and so without loss of generality, you can start and put this here, and any solution can be rotated so that this is on the bottom. Okay, so that's and it's the general principle about combinatorial problems in general that I call factoring. Okay, now, but got to keep moving. So let's go on to. All right. So to do Soma cube, I have items are the different pieces and the different cells. And so the different options are to say a W, use piece W and fill cell 212, 213, 222. All these options, and so it works. Okay, now let's go to another kind of problem, and this was well. Let's see. I got in here. There was one of the great masters of combinatorial mathematics was Major Percy McMahon of the Royal Artillery, and he was was the greatest combinatorial mathematician of the early 20th century. And in 1892, he had this patent on a game. Plans to use it in playing a new kind of game, and basically he had 24 triangles, and each triangle was numbered 0, 1, 2, or 3. You could think of this as 4 colors on the edges of the triangle, and he wanted to put these 24 triangles together so that edges matched together. And he became president of the London Math Society, and anyway, in 1921, he came out with this book about mathematical pastimes, and one of them was his problem on not on triangles, but on squares. So again, he has 24 squares, and this time there's 3 colors instead of 4, but there's exactly 24 different ways to color the edges. With 3 colors, with 3 given colors, and then he puts them together. So I got another another set of tiles here. This is for McMahon's 24 things. It's arranged with here in a 5x5 grid instead of a 4x6. But the 4x6 problem was the one that McMahon did. And I mentioned it because it has an interesting connection to Stanford AI Lab. One of the very first reports of the Stanford Artificial Intelligence Project is memo number 12 in 1964, and I believe it was the first large computation ever taken in Stanford's AI department. Documentation of the McMahon squares problem, and so he sets it up, and he has a computer program to count how many solutions there were, and the program ran for 40 hours, and he says right here, total of 12,261 solutions exist. And so this number, 12,261, was quoted in lots of publications throughout the 60s, and so on. It turned out that it was wrong, and in I think it was 1977, a man in Argentina, he's actually the rector of a technical college in Buenos Aires, recomputed it and got about 4,000 more solutions. This program had long gone, so we have no idea what the bug or bugs were in this program, but I had to mention it, as a piece of history. Okay. Well, it sets up very, very nicely but not as an exact cover problem of the normal kind. So here's a very important point. I'm extending the exact cover problem to something where I say exact cover problem with colors, or with color controls. And so this is really what I want to show you, especially this new kind of a combinatorial problem. Well, it's not exactly new, but it's. I'll try to explain why I think it's important. So it goes beyond what I've said before. So the items for McMahon's squares problem. There's an item for each cell, and there's an item for each kind of thing. But then I have, after the line, I have these secondary items, and I have a secondary item for each horizontal edge and each vertical edge in the diagram. And now with this new kind of problem, which I call an XCC problem, that's exact covering with color constraints, XCC. If you think of a better name, we might not be too late to change it, but anyway, XCC has been working for me for the last 3 years. So XCC problem says for every secondary thing, I can give a color to it, and that means that you can use the secondary item more than once. With the Queen's problem, I was only using those diagonal items at most once, but I didn't give them colors. It was as if in every option of that problem, as if I had a new color for every option. But this time, I can say this secondary item, the vertical line number 00, is color A. and this secondary item is color A, and this secondary item, and so the different options I have are to take one of the pieces, like the BBBA piece, and I can rotate it different ways, and I can put it in a particular place, and that gives colors to these things. So the rule is, on the primary items, you have to cover a primary item exactly once. On the secondary item, you're allowed at most one color. You can use the secondary items more than once, but if you do, they all have to have the same color, and that's the rule for an XCC problem. Now, I didn't realize until a year or so ago that I think it was a year and a half ago, how widely I kept solving more and more problems, that XCC problem, but I didn't realize how general it was and so I want to convey some of that to you tonight by further example. And so one example I have in my book is based on another popular recreation that you find in magazines and newspapers. How many people know word search problems? Have we seen word search problems? We got a few. Okay, so on page 23 of my thing, I got this problem here. Find the mathematicians. So put ovals around the names where they appear in this 15 by 15 array. Abel, Bertrand, Borel, Cantor, Hensel, Hermite, and so on. And they can appear either left to right, like here's Catalan, or they can appear right to left, and they can appear diagonally up or down. So there are 8 ways a name can appear. And I say here, take a break before reading any further. Spend a minute or two solving this puzzle. Because then you'll get the idea for why this is unnatural for exact covering with colors. Okay, so on the next page, there's the solution. Look at that. Catalan and Landau were both there. Here's Audemars upside down. Okay, and so on. So that's it. Now, the question is, of course, not how to solve this problem. This puzzle, is just determined. You just go scanning it. You don't. It's sort of no-brainer. You just have to look at 8 passes, for example, and you found them. But the problem is, how do you design the puzzle? How do you pack all these names in here? So for example, let's suppose I have a 6 by 6 array, and I want to fill this array with 12 words, O-N-E, T-W-O, T-H-R-E, 1, 2, 3, 4, spelled out all the way up to 12. And so, for example, here's 12 at the bottom. Can you read that there? T-W-E-L-V. Is that too light? And 6 is there, but if 11 is up here. Okay, so I had to pack all of those words into a 6 by 6 array. How could I do it? and also with one space left over. And so I set this up as a I have a problem that a driver that takes any word search for a 6 by 6 here and fits in a dot for the empty space, and then 1, 2, 3, and puts it in. How do you do it? Well, it's just a color problem where I have to cover 1. I have to have a 1 somewhere. That's one of the options, is to put it here, here, and here. All right, so for each option that I have for putting in O-N-E, there's a line here, and similarly for T-W-O, and as long as the colors don't conflict, I'll get a solution for this packing problem. Okay, so besides these word search problems, there's also word cross problems. So that's exercise 185. Let's see here. So here's an example where I packed 1, 2, 3. I even have 0 in here, 0 up to. But here, there are different rules. They all have to read like in a crossword puzzle, left to right, or across or down. And so I'm not allowed to. I got to have spaces between words and things like that. So another packing problem, as it turns out, sure enough, that packing problem can be done with XCC problem. Here it is. So I have, I have different items that have to be covered, and then the different ways, the zeros and ones say, do I have a space here or not, or a letter? Okay, so that's complicated, but it's there if in the book if you want to see. So now let me go to what many people consider the sort of the most important class of combinatorial problems, called CSP problems, the constraint satisfaction problem. And the model for constraint satisfaction problem is that you're given a bunch of variables in different domains, and you're given relations between the variables that have to be satisfied. And so there's many conferences organized around CSP. There's journals devoted to CSP, and the same model of CSP also it's equivalent to the model of joins in databases, and it's equivalent to physicists' models of interaction between molecules and things like this. So it's a very general problem. It turned out to be a special case of the XCC problem. So let me try to explain. Here's EZ-CSP. So constraint satisfaction problem. Let's say the variables are A, B, C, D, E, and F. Each variable is ternary, has a domain 0, 1, 2. The first constraint is that A, B, and C have to be in cyclic order. Also D, E, and F. The third constraint is C has to be less than or equal to D, and fourth constraint A less than E. So now let's set this up as an XCC problem. A line that begins here is a comment. Constraint 1 says that A is 0, B is 1, C is 2, or there are three ways to fulfill constraint 1, and I look, those are three options here. A, B, and C are cyclic. There's three options for D, E, and F. They're cyclic. There's 6 options for C and D because C is less than or equal to D. So C, they could be 0, 0, 0, 1, 0, 2, and so on. And the fourth constraint, A less than E. Okay, so that's, in general, when people have CSP, they have ways of abbreviating constraints, and so saying that these are all different or things like this. And there are also tricks to encode that with XCC. But in general, you see that the sort of generic CSP is a special case of this coloring problem, and the options are a very particular kind. Each option has only one primary item, and all of the secondary items for that primary item are in the exact same variables, the exact same secondary items. So the extremely small class of XCC problems actually covers all of the CSP problems in that sense. Okay, so now here's another another example well, I'm going to have to move faster, but one of the classical problems of computer science is called of combinatorics is to find a De Bruijn sequence, and this is a sequence of zeros and ones that contains, as its subsequences, it contains every possible n tuple, and you can generalize that and say, let's see what I have a page to show it here. Oh well, yeah, page 28. So. No, I have. I talked about XCC. We can go beyond XCC as well. And instead of saying that I have to cover every primary item exactly once, I can also say no. Let's let's cover it a range of times. Let's say that that the first primary item should be covered either once or twice. The next one exactly 5 times. The next one once through 8 times, and things like this. So I call this an MCC problem. This is a problem with color constraints and multiplicities. And one example of this is what's called the partridge problem, because Bob Wainwright was singing on the 12th day of Christmas, my true love gave to me, and he had various partridges in a pear tree, and so he said, well, it turns out that the sum of the first n cubes is the square of the sum of the first n numbers, which says that I should be able to take a 1 by 1 and 2 2 by 2s and 3 3 by 3s and so on, and n by n's, and put them together in a square. And it turns out you can't do that until n is 8. But here's an example where you have 8 by 8 squares and 7 by 7 squares and 6 by and so on. He called this his partridge problem, and you can solve this very nicely as an MCC problem by saying that you cover the 8 guys 8 times instead of once. All right. So I also could generalize de Broglie sequences so that I have a sequence that for let's see. It turned out this problem had 50,000 solutions, but I show you the first solution. I want to get all 4 tuples in such a way that if there's 1 1 in the 4 tuple, it occurs once. If there's 2 2s, it occurs twice, and so on. So here's a 32 cycle. 0 0 0 1 and so on, repeats every 32 times. Starting at 0, I got 0 0 0 1. Starting at 1, I got 0 0 1. So here I listed different times, and so if something has 2 1s in it, it occurs twice in a cycle. If it has 3 1s, it occurs 3 times in a cycle. Very easy to set this up as an MCC problem, and we get all the 50,000 answers. All right. Well, I see that I'm way over time, so I just got to show you. Maybe I ought to save this to next Christmas. I don't know, but I have so many. There are so many things I wanted to do, show and tell. So I'm just going to go through quickly now and just show you, because all of these problems use XCC mostly, and sometimes MCC, and so that's why I say I was like a kid playing with a new toy. And so I'm going to just run through quickly now, and you can go online and look at any of these that you're interested in. Here, for example, are some word problems where I got, I call them word stairs, and this is a cyclic arrangement of words so that you can read them across or you can read them down, and it makes words both ways. And here I could do it so you can make the stair go this way or the stair go this way, and here you use the same words, and either way you get different words, but it all works. That's an easy XCC problem. Exercise 178. Well, this was application to music. If you want to compose beautiful music, 12-tone system. Okay, I talked about McMahon problems, but that's just the beginning. Oh, I'm sorry. For example, there's a set of 24 tiles that McMahon didn't think of that turns out to make some really fascinating problems. That you can match edges, vertices instead of edges, and that gives you some really tough problems. Here you can match both vertices and edges. You can also use hexagonal grids. There's three-dimensional matching of faces on cubes. Okay, now on page 83, I have more about the n queen. So besides finding all solutions, it turns out that I forgot to mention it. DLX2, which does this coloring problem, is almost the same as DLX1. I could use all that code and just add a couple more subroutines to put on this color constraint. But then there's DLX5, which also says find the minimum cost solution. So instead of finding all solutions, it finds the solution that minimizes some cost. And for each option, you give it a cost, and then it chooses options that have the smallest total cost. And so here I took n queens, and I gave a cost saying putting a queen somewhere is what's the distance from the center. And so you find the solution to the n queens problem that have the shortest distance to the center, or the longest distance to the center, or in this case the shortest. If you take the nth power of the distance and let n go to infinity, then you get these patterns, which I believe are the most beautiful. I got problem. There's some delightful pieces called windmill dominoes. There's 10 of them, where you take an ordinary domino and you put a half-size domino at a 45-degree angle above it. And then there are lots of fascinating things that you can do to put them together, so that, for example, you get a path for both colors. In this case, it gives you a good path on the top, but not on the bottom. Here, it gives you a good path on the bottom, but not a loop on the top. But if you're clever, you can get loops on both sides. And so then there's problems about Mondrian dividing rectangles into rectangles. And then I finish it with puzzles that appear in lots of books and magazines. First of all, there's Furoshiki, and then there's Ken, and there's Slitherlink, and there's Masu. All of these are just as fascinating as Sudoku, and probably more. And there's Hidat, this is Kakuro, and this is Hidato, and Hitori. Anyway, these are all, I like to think that these pages contain the best write-ups ever made of those 7 puzzles. But anyway, it was great fun to write about them, and they all involve pi somehow. Oh, okay, well, here I am, 8 o'clock, so time to go and wish you all a Merry Christmas. But I hope I've explained to you why it taken me so long to finish this particular part of Art of Computer Programming. But I really think that the DLX solvers, I can't see why this isn't going to become kind of a new thing. The old, there's already $billion industry for CSP, but this goes a lot further, and it seems to have lots of potential. So I kind of feel that I'm trying to introduce it, and it looks like it might have a really bright future for people having better and better DLX solvers as time goes on. Thanks for your patience. Okay, well, don't feel bad about walking out, but I want to take it just one question anyway, and then I can handle other questions afterwards. So who's got a question that they wouldn't mind having online? Yeah.
One of the exact other things which you consider the games that students play.
Yes.
Do you have a good characterization of what kind of exact other problems are fun to play?
No. No. But there are some that are obviously more addictive than others. But the ones that I gave only 7. Nicole has an encyclopedia of 200 puzzles, okay, but I took the ones that are most popular, but also most different, because each of those 7 used a different technique. So I learned something with each of those. There was another thing that I could do with XCC that I didn't know I could do. Okay, thanks a lot.